Hey, good afternoon. Hopefully everybody can hear me. We'd like to thank you all for joining and being part of the conversation today. My name is Jennifer Berryman. I'm the Chief Communications Officer at UMassChan Medical School in Worcester, where we are laser focused on the future of medicine in some ways that we think might be surprising to some of you. We're going to hear today from Dr. Terry Flott. He is the Provost at UMassChan, the Dean of the T.H. Chan School of Medicine, our Chief Research Officer. He wears a lot of hats, so you're in for a treat today. He's a leading gene therapy researcher, and on top of all of that, a pediatric pulmonologist by training. So the big news out of our medical school, UMassChan, recently is that one of our faculty won the medical school's second Nobel Prize. Can you tell us a little bit about what the feeling is on campus?
Well, I think the best word for it is ecstatic. These are transformative moments for us, and the celebrations were spontaneous, exuberant, and really, I think, permeated a sort of a feel that essentially everyone in the community was part of this, and students were saying, "We won the Nobel Prize."
It certainly did feel that way. What did Dr. Ambrose, or Victor Ambrose, and his collaborator Gary Ruvkin at Mass General were co-recipients of the Nobel Prize in Physiology or Medicine? What did they discover, and why is it so important?
Well, they discovered the microRNA pathway, and I think hearing how they happened upon it is really illustrative of how science works. So they were studying C. elegans, which is a worm. It's an elegant worm, so to speak, that is very, very well characterized. Every single cell in the C. elegans body is mapped and tracked over time, and the development of this worm is extremely well described. So when some worms who had genetic conditions induced sort of DNA damage and genetic conditions, some of them had a fault in their program, the program for development. They were looking at what these genes were, and the thought was that genes encode messenger RNA, and messenger RNA produces a protein. But they found that one of these important genes, the LAT4 gene, it does not encode a protein. And when they looked at what the RNA was coming off that gene, was not a messenger RNA. It was actually a much, much smaller RNA, the kind of thing that maybe some people might have overlooked or discarded. And so these little 22 bases in a row, and another one that was a bit longer at 61 bases, these were instituting a really important developmental program. And it wasn't clear how they did that, although it was clear that they were interacting with another gene, LAT14, and I think the understanding that the microRNAs from the first gene actually could silence genes, other genes, through a mechanism that had never been seen before. That basic finding from that worm was then found to be a mechanism that is operative throughout life, including right in you and I.
So the seminal discoveries were made in the 90s, right? And
93,
was
yeah.
93. And was it clear at the time why it was so important, or what the implications might be?
Well, I think that part of the discussion that came shortly thereafter was whether this was peculiar to worms or whether these kinds of RNAs were present in other organisms. And so, the organism most people care about, which is human beings, actually, when people looked, they found these small RNAs, which I think previously they had been discarding because they were too small to be a messenger RNA. So once it was determined that these worked throughout all forms of life and in humans, of course, then people began asking, could they be implicated in disease or normal processes? And slowly that kind of came into focus that, yes, this is a major mechanism for regulating genes.
It's tremendous. So in his remarks on the morning, October 7th, the morning of the Nobel Prize announcement, Dr. Ambrose said, quote, "This is a great state university, and I wish everyone who lived in the state knew that they can take proud ownership in what happens here." What do you, as the provost and dean, wish that people knew about UMassChan Medical School?
Yeah, well, sometimes I hear it said, less often recently, that we're the best kept secret in academic medicine. We don't really want to keep it secret, so we hope people will be certainly paying attention. We are a major research university. We garner NIH funding at a very high rate. As you know, more NIH funding on the medical campus alone than more than 20 states. And then the quality of the science is proven again and again by, we have a dozen different faculty who've been appointed to the National Academies of Science or Medicine. And of course, the two Nobel Prizes in just about 50 years. Also, we have a very dynamic educational program, and I think the niche that we fill as the public university in Massachusetts is really unique in that we're doing our best in every way to create a great experience to train physicians, nurse practitioners, and scientists.
And we'll talk about that in just a minute. You touched upon research and NIH funding of research, which, again, Dr. Ambrose spoke about the importance of that in his own career and also to humanity in general. How do you think about that? And I guess what would your case statement be about funding for the NIH?
Well, as you said, I'm a pediatric subspecialist. We work with kids who have genetic diseases. And really, I think what these families are looking for is hope. And I think research is the hope for a better outcome, the hope for a better tomorrow. And in this country, as people in the Boston area know very well, most of the best research is done inside of academic medical centers, medical schools, and teaching hospitals, where most of the research is funded by NIH. So we really hope ourselves that the Congress will continue to recognize that value directly a value to human health and life, and also to our world competitive advantage in biotechnology.
So part of the future of medicine are the scientists, the nurses, and the physicians that will be the workforce of the future. And many of you who might have tried to get an appointment with a primary care doctor or a specialist recently know that there's a dearth, in pretty much across the board, and that more providers are needed. So UMassChan, you mentioned, is the only public medical school in the state, home to 3 graduate schools. How are you prioritizing the training and the bolstering of the future workforce?
It's a great question. Actually, I didn't mention this before, but I just came back from the AAMC conference. That's the Association of American Medical Colleges. All the medical schools and teaching hospitals go there. And we got an updated workforce projection, and the projections go as high as 60,000 physicians shortage by 2050. The forces are pretty obvious. We have aging of the baby boomers. People are using more health care as they get older, and it's hard to keep up with that need, not just in primary care, but also in the specialty. So we've focused on maintaining our dedication to primary care. We're the #1 medical school for primary care education in the Northeast, and on expanding the class size. It was very interesting when they talked about, in the workforce study, the impact that medical schools increasing their class sizes had. And it's actually, in the big picture, a really small percentage of the need. So we've been able to more than double our class size and maintain the quality, the outstanding quality of our students, and their dedication and idealism.
there's a huge demand there are a huge number of applicants, I should say. There are a lot of people who would like to be physicians. So how big is the School of Medicine class now?
The class size this year is 235. Our long-term estimate will keep it around 225 students. And there's well over 5,000 applicants for those positions. Many of them are from New England, from Massachusetts, but many are also from California, New York, or throughout the United States. And we've kept this core of what we do of about half of our, actually a little more than half of our students will always be Massachusetts resident students as the state's medical school. But at the current time, roughly 125 Massachusetts residents and another 100 that are out-of-state students.
And the medical school has a number of pipeline programs to make sure that a diverse array of people are preparing to be providers.
Absolutely. Absolutely. This is something we care a lot about because, you know, we are trying to train the physicians who will serve every community in the Commonwealth and beyond. And there we can talk about disparities of distribution of physicians and not just the total number of physicians. And minority serving institutions and minority neighborhoods are often underpopulated with physicians. They tend to crowd in denser, higher income areas. So we've learned that if we recruit students from diverse communities, they tend to go back to diverse communities. And that recruitment has to begin prior to medical school. We are committed to pipeline programs that draw from across the country, as well as to early STEM education right there in Worcester in our neighboring schools.
So I want to change topics and talk a little bit about something that you're a foremost expert in, gene therapy. UMassChan has really become a destination for developing gene therapies for rare diseases and is doing a number of first of its kind, first in human clinical trials. Why is that important?
Well, you know, when Chancellor Collins and I started back in 2007, it was right on the heels of Craig Mellow's Nobel Prize. There was a lot of excitement across the campus then, as there is now. And there was an opportunity to leverage that to take the institution to the next step. And one of the key things that under Chancellor Collins' leadership we decided to invest in was a group of scientists and physicians who were really dedicated to taking all the science that we had accumulated and helping to translate it, bring it to patients, to create innovative new products that could go into patients. And since many of us who assembled there at the time were very focused on genetic disorders, single gene disorders, we really tended to accumulate groups focused on that. Many of those are neurologic disorders, so we did a program developed in ALS, and then based on work of other key scientists we brought in, a program in Tay-Sachs disease, which is a well-known, although rare disease, more common in Jewish communities in this country and in Israel and around the world, and a very related disease called Canavan disease. Now, the patients with Tay-Sachs and Canavan have what we call a neurodegeneration disorder. So what that means for families is they have a baby that is born looking normal and starts out developing normally, and then sometime in the first year of life they start to slow down and then maybe lose some things that they were doing. And untreated, these disorders are tragic because then these patients undergo a rapid downhill loss. They start to have seizures. They're not able to do things like feed themselves by mouth. They can aspirate. They can't really control swallowing very well. can't walk, and they eventually lose sight and hearing. It's just, I can't even tell you how tragic these stories are. And so I think a group of the scientists and physicians really want to make a difference, really want to turn the tide on the course of those types of diseases.
So maybe we should zoom out for the benefit of lay people who might be listening. When we talk about gene therapy, what is that? We know that scientists know that there is a defect in one gene.
Yep.
And so what does the gene therapy try to do?
The simplest form of gene therapy is when you have a recessive genetic condition, meaning you're just lacking, that gene doesn't have the right code for a messenger RNA that'll make a protein. So you're really just missing a function in the cell. And that's the easiest one conceptually, because what you do is use a vector, a vehicle, to put a normal copy of the gene back into the cells where it is needed. So that's the gene replacement therapy. And really, I think some of the examples we've worked on first have been like that. Genes that have more complicated mechanisms may require things like siRNA, which really derived from Craig Mello's Nobel Prize and from Victor's, or even gene editing. And we're working on all of those, but I think the gene replacement examples are the furthest along.
Thank you for that, on behalf of the lay people. So you mentioned Canavan disease. That is one of the rare diseases that is known to be caused by a single gene defect. And one of the first in human gene therapy trials that was carried out by a local company using discoveries made by faculty at UMassChan. And one of the first patients was a little girl from Boston. Her name is Noah. And I thought that we could share a brief video with all of you to share Noah's story.
Noah was born in August 2020, so right during the middle of the COVID lockdowns.
Okay, ready?
From the beginning, we knew that there was something going on with Noah. By about 6 weeks or so, she was just crying all the time. By about 8 weeks, we were concerned that there was something wrong with her vision. She wasn't looking at us, she would look through us. That then led to concerns about weight gain. She wasn't gaining weight appropriately, concerns about her missing milestones. And we really had a hard time connecting all the dots. At 11 months, we were able to have her have an MRI, which is when she was able to be diagnosed with Canavan disease. When we got that diagnosis, it was like, oh my God, this connects all those dots.
Canavan is such a rare disease. It's a couple of hundred, maybe, people in the whole wide world.
I started working on Canavan disease in 1989. Then, in 2017, we developed our clinical usable gene therapy vector.
The day we got the diagnosis, she said to us, but there's a trial. She's like, they're enrolling kids. We were like the first family to be given this idea that there was something that you could do. All the other families were told, just go home and love your kids, there's nothing to do. But for us, it was, there's a trial, there's something on the horizon that's actually could make a difference.
From when she got gene therapy to now, which is a little bit over a year now, this is not the child that was on the trajectory that she was on in June of 2022 when she got dosed. And to see her now, she's walking. Canavan kids don't walk. Canavan kids don't sit like this.
This is probably the first time I saw what I've never seen before. I feel very emotional.
We used to have to worry a lot more about her.
We can never, ever, ever thank them even close to enough for what they have done for our family.
And this is Noah, just a month or two ago when she started K1, 2 years after she got gene therapy for Canavan disease. So, Terry, what does that tell you, this story?
Yeah, I mean, I still can't look at that or meet with her and the Greenwood family without saying wow. So, I mean, this was really a dramatic, successful response. Of course, everyone involved, Dr. Gao, who really pioneered this, discovered that gene in 1993. We're all so thrilled on their behalf. I mean, I do have to say a lot of the patients in these trials don't have as dramatic an effect yet. This is very early in perfecting it, but it shows that it can be done, and talk about, giving hope to families. I think, people talk about like how long it takes, how much money it takes, but one of the things I think we should keep in mind is it really takes the commitment and the courage of these families to say, okay, well, we're going to volunteer and have our baby participate in a gene therapy trial, which in fact does incur significant risk. But all the families I have worked with and that we've seen as part of all of these programs really are dedicated not just to giving their own loved one, their own child a chance, but to do so on behalf of the greater community as well. And we're just really blessed here, in addition to the wonderful people at UMassChan, the wonderful, talented faculty we brought together in Boston. We have so many great institutions, our colleagues at Mass General, other places that we collaborate with a lot, and of course the whole ecosystem of biotechnology, gene therapy, and gene editing in particular. There's really not a better place on the planet to have this kind of opportunity, this kind of hope for the families.
You raise a good point that none of this happens without the families, but also without that collaboration between public, private, academic.
Absolutely. I think that it is actually quite inspiring to people who are involved to see these kinds of results and realize that what we're doing is not just a way to make another successful product in the marketplace. This is really about changing the lives of people who are suffering. Now, rare diseases, you might say, well, they're rare. Couldn't you help more people doing other things? But there are a total of at least 7,000 rare genetic disorders, other rare disorders beyond that. And cumulatively, this is a very large number of patients in the United States that have these rare diseases. And so we also hope that what we learn with the Tay-Sachs patients, Canavan patients, that'll help us with other disorders that are rare.
When you add up all the rare diseases, 1 in 10 Americans.
Yeah, it's just astounding, isn't it?
Just quickly before we wrap up, the pace, we often hear about the pace of science, that it takes decades to get a discovery made in the lab to a place where it can benefit people. Is that changing? Is the pace accelerating?
Yeah, it certainly is. I mean, I think probably the best example is if you look at how quickly CRISPR-Cas9 was moved forward from its discovery around 2012 as a potential therapeutic to having FDA-approved products and many other CRISPR-based products in the clinic well before by the end of the decade of the teens. So it is going somewhat faster. It would not be able to continue this momentum without a combination of all of those inputs, not just the collaboration of the individual scientists and biotech firms and physicians, but we really need investment from the federal government. These breakthroughs were accelerated once they hit the clinic, have been accelerated by private investment. And we're really concerned, I individually am quite concerned that, that the pace of progress has historically slowed down some when there is less private sector investment in technologies like these. So we hope that all these factors continue to push in a positive direction. Because, you know, if you have another genetic disease that's not Canavan or Tay-Sachs, like Canavan or Tay-Sachs, I mean, I get contacted by people with other diseases, rare diseases that some of them only have letter number designations, and they say, well, why can't we apply that technology to our child? And in theory, you can, but expanding that access, making the time point from when you decide, okay, this is a gene we should put in, making that shorter and making the cost point lower, is really important to speed access to this technology.
Terry Flatt, thank you very much for your time. In closing, I just want to mention that if you enjoyed hearing Noah's family's story, you can hear more from the Greenwoods and other families like them who are facing rare diseases. We're working on a special podcast series that will come out in February, which is Rare Disease Month. It's called Rare Diseases, Real Stories, and we hope that you'll look for that in early February. So thank you.